Jeremy just received his PhD at Northwestern, which is a big accomplishment, so congratulations.
Thank you.
Yeah.
Thanks.
So in this talk, Jeremy's going to provide a user-friendly introduction to mathematical optimization for machine learning by answering 3 important questions. What is mathematical optimization? Why should a machine learning researcher practitioner learn it? And how does it actually work? Okay. So thank you, Jeremy.
Thank you. All right. I'm going to try to make sure this thing doesn't fall off my ear. Can you hear me okay? Yeah. Is that okay? Okay. First, let me just show you the GitHub repo where you can find all this stuff. Which one can you see? Is it this one? Oh, okay. Ah, okay. Let's see. Oh, you can see that. Can you see this? Huh? Hello? Ah, it's one of those. Now I gotta go like this. Okay. Cool. You can find all of the stuff I'm going to talk about today, including the presentation in a PDF and the Jupyter notebook, on which I'm going to run a bunch of demos, and the backup files that basically just plot a bunch of stuff and make nice pictures. At this GitHub repo, it's a GitHub, okay, germwatt ML refined. If you go there, there's a subdirectory that's depy 2016. Again, it'll have the presentation and all of this stuff in it. And what stuff? Okay, where's my? Okay, I always feel discombobulated. Okay, let me get. There we go. Okay, yeah. So my name is Jeremy Watt. I'm going to talk about mathematical optimization for machine learning. It's going to be a high-level talk about what mathematical optimization is, why you need it in machine learning, and hopefully give you some intuition about basically how it works, generally speaking. This talk is based on a textbook that Reza, Borhani, and I wrote. We're just finishing the final draft, actually. It should be on the shelves in July or maybe August of this year. It's called Machine Learning Refined. It was developed over a period of years while we were PhD students at Northwestern. We used it to make and teach a bunch of original classes up there. That's just a picture on the right of one of our large machine learning classes, and I don't know who. That's probably me in the background, a big, bald, white guy. So yeah, it's kind of our baby. It's a very unique textbook in lots of different ways. We like to use pictures to explain things, as you'll see today. There's lots of cool pictures, lots of geometric motivation and intuition for a lot of things I think people are commonly confused about. At least personally speaking, I was confused about before writing the textbook and really digging into things. And then a lot of Python examples and code, which I think a lot of machine learning textbooks tend not to have that kind of stuff. It's published by Cambridge University Press. Half of it is available online at our website at mlrefined.com. There's code there. If you click on this tutorials thing, you'll find some tutorials from other conferences that we've spoken at. And then if you click on the code thing, that'll take you to our repo, and you can find the depy code here as well. It's mlrefined.com. Okay, so enough advertising. So the intended audience for this talk is I think, pretty broad. We hope that you know something about machine learning. At least maybe you've heard some jargon words. But in addition to that, like you're just at least a little bit comfortable with function notation. Like function with a scalar input, like g of x, okay? And then also, obviously, you know Python, and you're familiar with the Python notebooks, because I'm going to do various demos in the Python notebook, and if you've used that before, it makes things a little bit easier to understand. So that's the intended audience. The outline is we're going to motivate optimization for machine learning just using the simple linear regression problem, okay? Which I assume a lot of people are familiar with. We're then going to talk about how do you seek out the best parameters to a linear regression from a calculus or mathematical point of view, then talk about the big picture on mathematical optimization, exactly how do these algorithms work from a bird's eye view, and then go deeper into one of them, probably the most popular one used in practice today, from everything from linear regression, linear classification, to neural networks and deep learning, an algorithm called gradient descent, okay, which is totally based off of a fundamental calculus fact, okay? So linear regression, this is going to be important because, well, actually we'll see. So here's what linear regression is, right? You have a bunch of data. In this case, this is a data set of total student debt in the US. Along the horizontal axis, you have the year This is taken from the Federal Reserve in New York. Along the horizontal axis, you have your input, which is year. Along the vertical axis, you have total U.S. student debt in trillions of dollars. Okay, and with linear regression, right, we want to fit a line to a data set, say like that. Both because we want to represent it with a functional form, and also because we want to be able to make predictions, like say what would be the total student debt in the year 2016 if this trend continued. Right, so that's linear regression. How do you derive the cost function or the way in which you find that line? So this is what optimization is used for universally in machine learning, finding the right parameters for a model. Okay? So I'm just going to walk through very quickly the formulation for a least squares cost function for linear regression. That is the cost function that you derive in order to tune those parameters properly, and in this case those parameters are the slope and intercept of the line that you fit to the data. Okay? So you start off with a collection of data like the one shown on the right there. Your input, the input axis is x. Okay, that's the input variable. The output is y. Okay? And in particular, we have a collection of, say, big P could be like 20 or 30 or whatever, big P points that are input-output pairs. So that is, we have an input, okay, xp, right, that's the little pth input, and a corresponding little p output. Okay, that's our little p input-output pair. Okay? We want to fit a line to that. Okay? And if we have one-dimensional input, it's a line. In higher dimensions, it's a plane or hyperplane. Okay? The equation of that line, just to introduce you to some of the notation we'll use, we're going to use b as the intercept, right, where that thing crosses the y-axis. X is the input, right, and w is the slope of the line. And we want to find b and w so that b plus xw equals y fairly represents that data set. Right? Oh, and I should say, sorry, you can, I don't know how this works because you guys are in charge. If you want to interrupt me at any time, you should just yell at me. I can't see any of you, okay? I assume you're all naked or whatever, you know. Okay. So we want to find b, the intercept and the slope, right? And in particular, we want to find b and w so that that line fairly represents the data. Well, what does that mean from a mathematical standpoint? Very simply, it means that for each input xp, when we run it through that line, we should essentially get its output, yp. Okay? Or in math jargon, right, b plus xp, the input, times the slope should give us essentially the corresponding output, yp. Okay? We want that to be true for all of the data points in the data set, not just the little pth one, right? Okay. So what do we do? Like, I mean, now that's the kind of the basic setup for linear regression. I guess I assume a lot of you guys have seen that. That's the setup. Like, that's what we want, right? We want a parameter b, an intercept b, and a slope w. Or again, in higher dimensions, you have more parameters, but the setup is exactly the same. Okay. You want those two parameters such that that condition holds, right? So that the points are fairly represented. But that doesn't tell you how you find those parameters, okay? You have to go one step further and say, okay, what am I going to constrain on the problem to recover or to derive those proper parameters that make that semi-equality hold for all of my data points, okay? What you do, or one way of doing it at least with linear regression, is to say, okay, I'm going to try to formulate that phrase in a slightly different way. I'm going to try to formulate it as, I'm going to take the difference between the left and right-hand side there and square it. And as you see, there's some now dotted lines. Let's see, dotted lines on the graph there. I'm going to try to minimize that error, and that error squared in particular, okay? So that it doesn't matter if I get negative or positive error, so I square it. So now we put that, sorry, I think I have a weird shaped ear. Yeah. Try to tuck it under my glasses here. There we go, okay. So now we just put that in mathematical frame, or sorry, we say that in math, right? So what is that? We want to minimize, we want to find the b and w that minimize the squared error between the corresponding line and the data. That means we should take the difference between both sides of that thing and square it, okay, for each of the data points. To say that we want to do that over all the data points, we can say, well, we want b and w to satisfy if I took that error and squared it and then summed over all the data. Okay, all of those dotted lines there on the right, we want to make sure the collection of those, when I sum them up, they're as small as possible. Okay, and that's what that says. The math version of that is just right there on the bottom left. The creature there that is describing, okay, the b and w that we want is called a cost function or a loss function in machine learning or statistics, okay? we can say in order to find B and W that fit our data set well, okay, now we have like another way of saying it, is we want to find the smallest possible value of that cost function. Okay, we want to find the parameters that give us the smallest possible value of that cost function or minimize it. Okay, because if we minimize that, then we've minimized the squared error between the corresponding line and all those data points, meaning we've made a pretty good fit to the data. Okay, so we want to minimize that cost function. Okay. Now let's look at a demo of that with in the notebook that you can find on GitHub. Where am I here? Okay. Aha, come, you go, what? Eh? Aha. This is, it's titled DePi 2016 Optimization Demos. This just contains all the demos I'm going to show you today. It's a Python notebook. Okay. So let's just kind of load things in here. So the first thing I'm going to show you, actually I don't even need to run it, but we can run it just to see that it works. This is that student loan data, right, that I showed you earlier. This is the corresponding cost function that we want to try to minimize, or it's a convex, or it looks like a cup or a half pipe, okay? We want to find the lowest possible point on that cost function because the parameters, right, this parameter is the intercept B and W, right, that cost function is a function of two things, the intercept and the slope. If we find the lowest possible point on here, that's going to correspond to a good fit to the data set, the right slope and the right vertical intercept, okay? And we'll come back to this in just a few minutes and actually fit the data and watch, you know, the algorithm will learn the proper parameters after we talk about how that's done at a high level, okay? Cool. Okay. So what is the search for ideal parameters, or the search for, say in the case of linear regression, the right slope and intercept? What does it look like? Well, like I showed you that picture for linear regression, and it's just true for all machine learning models, regression classification, PCA, k-means, neural networks, whatever you give me the name of something that you've heard of, all of them have an associated cost function like this for tuning parameters properly. And the way in which they're tuned properly is based on the following calculus fact, okay, that you probably remember, well, maybe you don't remember, I don't know how old you guys are. You know, okay, so the derivative of, you know, thinking about where the minimum of this cost function, this one-dimensional cost function, where that derivative is zero, okay, or where the minimum of that thing is, because those two facts coincide from a calculus perspective, okay. So remember from your early days of calculus, right, now I'm gonna strictly talk about scalar input cost functions, just so I can draw pictures of stuff, okay. But everything I'm gonna talk about from now on, it carries over perfectly for the case where that function has multiple inputs, like for linear regression, where I have 2, or any problem, neural networks, where I could have like 1,000,000, okay? It's the same game, but I just want to be able to draw pictures, okay? So say I have this cost function G, and the input is W, it's a scalar input, okay? And it looks like a cup, okay? I can look at a point V and the corresponding objective value, the cost function at that point. Remember that the derivative at V is just the slope of that tangent line there, right? That's the slope of the tangent line, okay? And in this case, it's negative because that thing is going downhill, right? So the slope is negative. Over here, just another point. Say I'm over here on the right side, V. There's the cost function value when I plug in V, that's the value. There's the tangent line at that point, and the derivative there, right, is the slope again, and it's positive, right? Because that line has a positive slope. Okay. Here, one more place, right? I'm down at the very bottom, right? That tangent line has a slope of 0, and so does the derivative. It has a value of 0 because the derivative is the slope of that line, right? So this calculus fact, like I said, is the basis of almost all numerical optimization algorithms that are used in machine learning and lots of other fields like economics and physics and all sorts of other stuff. It's the following fact that the slope of the derivative at minimum or minima is always 0, okay? And basically we design algorithms to try to find points like that, okay? Okay. So that is the fact that all these algorithms are based on, trying to find points that satisfy that 0 derivative, okay? Like I said, it carries over into multiple dimensions as well. If I have multiple inputs, it's the same game. Now the derivative is called the gradient, Okay, instead of the derivative, it's the gradient. If you've heard that before, it consists of multiple partial derivatives. Okay, but it's the exact, the analogous, it's very analogous to the scalar input. Okay. Now, okay, how do you find such points, right? You want to find, remember we're trying to like fit a, say, a regression line properly. We're trying to find the bottom of a cost function. How do we find it, or, you know, how do we use this fact in order to find that minimum? I'm telling you, well, that point has a derivative of 0, so we're going to try to find those points. Well, you can, okay, in simple cases, find those points by hand. That is by pencil and paper, by using kind of classical math, okay? But most cases, you cannot actually compute those things by hand. You need to use an algorithm to find those points, okay? So for example, like g of w is w squared, right, the parabola, okay? If I, first of all, you can see that the minimum there is 0, right? You can see probably the tangent there, the tangent line there has a slope of 0 as well, so that is the minimum, okay? If you can see it, okay, but if you take the derivative and set it equal to 0, right, the only point that's going to satisfy that is w equals 0, the minimum, okay? So that's just a simple example where you can actually do that, okay? In most cases, you cannot. In machine learning, in most cases, you cannot do that. And just to show you a simple example of something where it looks very simple, it's not that much more difficult than w squared. It's w to the 4th plus w squared plus w. It looks simple enough. But if you go to the, actually I shouldn't even go to the notebook. I'll show you the picture of the function. And just try setting the derivative equal to 0. This is w4, w to the 4th plus w squared plus w. Okay, the minimum you can see is somewhere around here, but try just like using calculus and set the derivative to 0 and solve for w. It's crazy. It's absolutely crazy. Okay? If you go to like Wolfram Alpha, you can see. Minimum of w, is it in there? Do I have it in my history? It is super crazy. W to the 4th plus w squared plus w. Okay, let's see. So something, you know, 0.385, yada, 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 okay? Something you're not really going to compute by hand. Okay, that's like something that obviously there's a numerical scheme, probably gradient descent, the one I'm going to talk about in significant detail today, running in the background there. Okay. All right, let's go back to those guys. Okay. Okay. But yeah, so the short of it is you can't use that calculus fact straight up, just using pencil and paper most of the time. You have to design algorithms to do that. Another reason why, you know, first of all, you can't solve a lot of those problems by hand. Another reason is like you can't see these cost functions, right? If you have lots of parameters, or even in a simple linear classification case, when you have 3 parameters, you can't visualize the cost function and just look at it and say, okay, there's the bottom. Okay, so you need some kind of scheme for finding those things. All right, here's the big picture on how the algorithms work, all of these numerical algorithms. You want to find that point. Right, that's where you're going to find the best parameters, say, for linear regression. Okay, you start off at some point w0. Okay, that could be anywhere. Oftentimes, you just choose it by just randomly. Okay, or if you're clever and you can figure something better out, you design that. But oftentimes, it's just totally random. Okay, you initialize at a point. You travel downward. Okay, to a point w1, right, along that axis there. And then you repeat that until you converge. I go to W2, okay, I go all the way to some WK where I've reached approximately the bottom, okay, or the minimum of that cost function G. Now that's the big picture, okay? That's where we wanted to go. So you basically travel downhill, you roll downhill until you reach the solution, okay? Now, I think one honest question to ask is, okay, how do I know which way is down, especially if I'm in like a universe where I have, say, like, 30 parameters as my input? Or common neural networks today, like you see things that are being solved at Google and Facebook and places like they have like millions, if not billions of parameters. So you're not, which way is down in like a billion parameter space, right? Okay, so that's an honest question. How do I know which way is down? I mean, I can see this thing. I know which way is down for a one-dimensional case, but what if it's 3, 4, or more? I can't visualize. How do I know which way is down? And how do I actually stop? Okay, so I told you stop at the bottom, but how does it, how in practice do the algorithms actually stop? How do they know when they get to the right place? Okay. The short answer is you use the derivative at every step of the way, and that's a gradient descent, or Newton's method. So just to show you an example of rolling downhill to a solution of a machine learning problem, where's my cursor? Oh, I'm losing it. Where is it? Yeah? Oh, I see it here. What's going on here? Aha. Huh? Okay, let me go here. Okay, what is... Sorry? You know what, I should just overlay these completely so that they... If I can actually find the thing. Okay. Aha. Is that going to do it? I see my mouse on this thing, on my cursor here is like stuck. Where? Okay. What the heck? Okay. Okay. Aha! Oh my God! Wow. Okay. Cool. All right. Sorry. So the issue is, give me an example. Show me, how rolling downhill actually solves the linear regression problem. Let's scroll down to one of these demos here. So you see in this case right here, this is a demo. We're going to look at how the gradient descent algorithm actually works in just a moment. But let's see if this. I gotta run. Make sure this is good. Okay. Come down here and run this guy. This guy. Okay, and then, okay. You see how it's rolling downhill? Okay, the algorithm rolls downhill, and as you roll downhill, the parameters start getting real good, okay? They get real good. But when you're at the top of that cost function, right, or when you're not really at the bottom, so notice how it has to like rotate around, okay? When you're not at the bottom, so the corresponding parameters can give you a very bad fit to what you're doing, okay? But that's in general how these algorithms work. You roll downhill, you take steps and you roll downhill. Okay. Let's keep the cursor there and never move it again. Okay. That's how they work in general, right? Let me just show this again. You roll downhill. You start somewhere, you roll downhill. Okay, and then the two questions are, which way is down, okay, if you're rolling downhill, and when do you stop? How do you know when to stop, okay? All right. So there's that picture again. Okay, so let's back up a few steps and just deal with that first question. Which way is down? Okay, how do we know which way is down? Which way? We don't. Okay, let's try to get at that. Well, what do we know about, say in this case, if we initialize, if you come with me, and we initialize a mathematical optimization algorithm whose goal is to reach the bottom of that cup, okay, the bottom of that cost function. We initialize at a W0, as shown there. How do we know which way is down at W0? That's the question, okay? Well, we can say, well, what do we know about G, about the cost function at that point, at W0? Well, okay, we know the value of the cost function, okay? That's this. Right? We know the value. We can plug it into the cost function. We know the value of the derivative. That is the slope of that tangent line, right? And as we're going to see, okay, it is definitely this. The fact that we know we can compute that derivative, that we know the proper direction of down at the point W0, okay? All right, why is that? Let's clear the plate. Well, notice that tangent line at W0 looks a heck of a lot like the function, near there, right? If you remember from your calculus, that is kind of the definition of a derivative. Okay, it's locally very similar to the underlying function, but it just visually, it looks the same. The tangent line looks very similar. So the question is, or the issue is, and sorry, it looks very similar across the function, right? That's what a derivative is. The question is then, okay, if we travel downwards on the line, does that mean we're traveling downwards on the function itself? And I don't know if you look at the picture and you kind of think about it a little bit, yeah, the answer is, okay, if as long as I don't travel too far, traveling downward on the line is pretty much like traveling downward on that cost function g. And why is that important? Because actually you can compute which way is down on the line. A line is like one of the simplest kind of mathematical objects there is, right? And we can very easily compute which way is down on the line, okay? And then we use that to go down on the function g, okay? So let's see, how do we know which way is down on the line? And this kind of holds in higher dimensions too, okay? All right, well, we can just visually see the slope, say at that particular w0, the slope of that tangent line is negative, right? The derivative, which is the slope, is negative. To go downwards, right, means we want to go in the positive direction then, right? Or in the negative slope direction, right? Or in the negative derivative direction. They're all saying the same thing, right? If the slope is negative, we want to go in the positive direction or in the negative derivative direction, okay? If we're traveling just on the line, that means, say, we travel to that point x, and that's good enough, if we hop back onto the cost function g, to help us travel downward on g, okay? So we take a step like w0 minus the derivative at w0, we're going to travel downward on that line, and therefore travel downward on the cost function too, okay? Now notice that I can multiply that direction by a constant to control how far down I travel, okay? And that's alpha here, okay? Some constant that's bigger than 0. If I attach that to the direction, okay, to the derivative, and I crank it up, I move further, right? Number 1, number 2, right? If I make it smaller, I travel not as much, lesser, if that's a word, right? I just don't travel it that far. So I can control how far I travel in that direction by putting a little parameter there, okay? And making w1 equal to w0 minus that direction, that derivative at w0, times a little constant that I can play with to control how far I travel, okay? And there you go. That's a perfectly logical way of using the tangent line, traveling downward on the tangent line to therefore travel downward at least one step on the cost function g. Okay? Is that cool? I can't see any of you, so I guess it's cool. It's cool? Okay. What if you go over here, right? You're at a different point. Does the same kind of formula hold? And yes, it does, right? The same intuition holds. What if we started off at this w0? Okay, well now the slope isn't negative there. The derivative is not negative at that w0, right? It's positive. Okay, so you just got to switch a couple signs around. That slope is positive, that derivative is positive. And to go downward on the line means we want to go in the negative direction, or to the left here, right? So we have to switch this around. But because the slope or the derivative is positive, taking minus the slope takes us in a negative direction, okay? So that step, w0 minus the derivative of w0 takes us still in the right direction, right? On the line, it takes us downward on the line to that point x, okay? And then if we hop back onto the function g, we've traveled downward on g, okay? We can then play the same game. Well, if I multiply the direction by some positive constant, can't I just control how far I travel on the line and therefore on the cost function itself? And the answer is yes. So if I multiply the direction by alpha here, there's the cursor. Then if I make alpha large, okay, I can travel a little bit further. If I make alpha small, I can travel not as far. Right? I can control how far I go in the downward direction by multiplying by that alpha. Right? Okay. Again, we see, if we started on the left side, W1 looked like that. What's in that green circle, right? The step looked like that to go downward, okay, on G. And then if we started on the right side, we still take the same step, right? Because of the sign of the derivative or the slope on each side of that thing. And it turns out this is like a pretty good way of going from W0 to W1 regardless, right, of where we start off. Okay, I showed you a couple pictures, but in your mind, I hope you can generalize, okay, basically regardless of where you started off there, the form of that step is totally cool, okay? And if it works for W0, right, then why not use the same intuition at W1 to go downhill a second time? Okay, so now I use the same intuition. I start off at W1, say. I draw the tangent line. I travel in the downward direction. What's the downward direction there? It's given by, well, the negative derivative at W1, right? That was the downward direction at W0. It's the same thing at W1, okay? What does the step look like? It looks like, well, now instead of W0, 0 minus alpha, the derivative of W0, I just plug in W1, because that's where I started off at. Right? And you can continue. Keep going like this. You can go all the way down to the bottom of that cost function, up to, say, some wk minus 1, the k minus 1th iteration of such an algorithm, right? Draw the tangent line, go downward. What does downward mean? Well, it means traveling in the negative derivative direction at that point. Okay, it's always that. Then the step, okay, looks exactly the same. Wk minus 1 minus alpha of the derivative at that point, right? And you finally end up, okay, at, say, the kth point at which you're approximately at the minimum of the cost function, okay, where the slope of that line is essentially 0. Now, notice what's going to happen when you get to that point. If we use this form of an algorithm, this form of taking steps downhill, right? If I then tried to, say I took a step and I finally got to this wk where the slope was exactly 0, right? If I tried to take another step using this framework, well, I would plug in wk right here. I would say wk minus alpha g prime of wk. But the derivative there, the slope of that line is 0, right? So I would just be saying wk plus 1 equals wk. So I won't go anywhere. If I'm at the minimum or I'm close to the minimum, the derivative is 0. So this thing doesn't take you anywhere, okay? So it both works getting you down the hill and it helps you stop. Okay, or makes you stop, you could think. Okay? That algorithm is called the gradient descent algorithm. Okay? The gradient, again, is like the multi-dimensional version of the derivative, right? So I could call that derivative descent. That's kind of what I showed you. But it works, the same thing holds if you have more than one input. Okay? Then it's called gradient descent more generally. Right, what do? You start off at some W0. You move downwards, okay, at the k minus 1th point. You move downwards like, well, I take that point and I subtract off alpha times the derivative at that point. That means I'm traveling downward on the associated tangent line, then basically hopping back onto the function. Okay? Then you repeat that until convergence. And oftentimes, what people do is they just set this alpha the same for every iteration of gradient descent. And maybe they play around with it a little bit to make sure the algorithm converges properly. Okay? Convergence here can mean several things. It's kind of it depends on your proclivities, okay, or what you think is best. So some people actually run the algorithm until the derivative at the point they're at is essentially 0. Other times people just run it for, say, 50 iterations and then, okay, that's good enough. I'm done. That demo I showed you earlier of linear regression that we're going to look at again in a minute, I just ran it for 20 iterations or something like that and just said, okay, fine, it's good enough. I'm done. I didn't check to make sure the derivative was exactly 0. Okay? Again, what you do here, what is the gradient descent algorithm? You start off at a point W0, right? You think to yourself, which way is down? Okay, well, I know that the derivative is the slope of the tangent line, and the intuition is, well, I can figure out which way is down on a line pretty easily. That's just the negative derivative direction at that point, okay? So you do that. You take a step downward on the tangent line, you hop back onto the function at W1, okay? You do it again. You start off at W1. Draw the tangent line, right? Go down a little bit, okay? Hop back onto the function, et cetera, until you get down to basically where the derivative is 0, okay? So the derivative, to answer the two questions of being, it both tells you, okay, which way is down, and then how do I stop? It kind of takes care of both of the problems for you, okay?
Question?
Yeah, totally.
If alpha's too big, you could possibly hop on either side of the
Absolutely. You're going to play with that in just a second and kind of see, yeah, how do you choose alpha in practice? Basically, people will kind of like, they pick a couple. Oh, sorry, can I repeat the question? The question is like, yeah, if you set alpha too big, aren't you just going to bounce around? And the answer is totally. And I'll show you a little toy demo where you can play with that fact. Yeah.
I could ask two questions. One is, very general, minimize problems. It's quite often that the gradient function is unknown. So
Mm-hmm.
is that very common in machine learning problems that the gradient function is already known?
Can I repeat? Is that okay? The question was, in machine learning, is it common that you can actually compute the derivatives of the function you're interested in? And yes. That's which makes it pretty sweet. Yeah.
Okay, so it is pretty common in machine learning, as you know.
Absolutely. Most, actually, sorry, I wouldn't say it's pretty common. It's like 100% of the time. Yeah. I mean, unless you're working on some very esoteric, like learning theory stuff, but say like, whatever, the research being done to like, at like Facebook and Google and stuff like that, none of that. You define explicitly the cost function. Like you design it. And actually, a lot of research is like, how do you design the best cost function for a problem?
Yeah, another question is, actually, by looking at this previous season,
Yeah.
there is in part there is you use the W minus the E prime W.
Yeah.
If without the alpha, then in general W and G prime W are not in the same unit.
Oh, not in the same what? I'm sorry?
They are not in the same unit.
Oh, can I, yeah.
Unless,
Yeah.
unless you use the alpha to correct the unit, or
Yeah.
you standardize W to make them unitless.
Yeah.
Otherwise, they cannot minus each other.
Yeah, yeah. So the can oh yes,
So
yeah.
in general, that people put the alpha with unit, or people just standardize W before they do anything.
Totally. And can I repeat just and correct me if this is correct. So the question was, what if like W and G aren't in the same units, and you're taking the difference right there between W and G, and like what that's like going to make nonsense basically, right? Thankfully, in machine learning, that never happens. W and G are always in the same units. Oh, I mean, I think I can say that universally.
So basically, when people design the W's, they are already unitless.
Yeah. I think that's true. Yeah, unitless. Yeah, because these cost functions, like the way I don't know if you remember the way I derived that linear regression one, right? Like, there's no units there really that you're worrying about. Typically, in order to kind of deal with that, people standardize the data first, so that they don't have to deal with that here. Yes, yeah. Oh, sorry. Oh, I don't know if is that a question. Sorry, I can't hear. Oh yeah, I'll talk about that in just a few minutes. So that definitely happens. This is this is like the simple case, right, where you only have the bottom is the only place where there's 0. Yeah, but that absolutely happens. You just wait like 5 minutes, and I'll show you pictures of that. Is that okay? Yeah. The question was, sorry, like what if you have functions that have multiple like points where the derivative is 0, where they're not minimum, right? And I'll just say, yeah, that happens, and I'll show you how gradient descent works in that case as well. Okay? Oh yeah, just yell at me, dude. I can't see anything. So yeah, so the question was, what about using Newton's method? Yeah, Newton's method is also highly used. The issue with why I'm using gradient descent, or why I'm presenting that today, is largely because I think it's a simpler one to motivate. You don't need to know what a Taylor series is. You just kind of have to remember that the slope of a line is the derivative, right? Newton's method absolutely is the bomb. And for a lot of cases that have like convex cost functions like this, it is absolutely the thing to use, okay? There are times in machine learning like where it's not appropriate, or it's not it's not necessarily appropriate to use Newton's method because of the growing size of the linear system you have to solve. So like, for example, if you're doing nonlinear regression and you have high dimensional input, I don't know if this jargon and stuff is going to mean something. You have to transform, if you want to do nonlinear regression, you have to transform that input in such a way that basically you end up with a linear system that is a P by P matrix, okay? And you can think, if I have 10,000 data points, I have a P by P linear system to solve. I can't even like store the matrix unless it's really sparse, or I do something, you know, to solve the linear system. And oftentimes, like, you're talking about like companies now that are trying to solve nonlinear regression problems where they have like hundreds of thousands or even millions of points. Newton steps become kind of problematic unless like you're really a specialist at numerical linear algebra, which I totally believe in. I believe in Newton's method. I'm not saying it's like bad, but off the black box version of it, it's going to have problems with issues of basically growing sizes of data and nonlinearity in machine learning problems, at least. Does that make sense? Or? I'm saying Newton's method's good, but there's problems in machine learning due to nonlinearity and very large linear systems, basically. Okay. All right, just yell again, because I can't really see hands or anything like that. Oh yeah, okay. So let's actually look at an example, okay, using gradient descent, okay. I showed you this function earlier. This is w to the fourth. Where's the cursor? W to the fourth plus w squared plus w. Okay. All right. Where am I? There we are. Okay, he disappeared. I showed you this function earlier, okay, and actually you can see I've already made a run of this. This is larger so that like if you look at the GitHub notebook, you can kind of see ahead of time what's going to happen, okay. This is a run of gradient descent applied to minimizing that one-dimensional function w4 plus w2 plus w, right, where I showed you when I went to Wolfram Alpha and I said, hey, try to like set the derivative equal to 0 and solve for that weird number, okay. But gradient descent can be used to solve for that. So let me come up here and just show you the form of the gradient descent algorithm. Okay, where am I? Okay, here we go. Here is the little snippet of code, Python code, to run gradient descent in order to minimize that function. Okay, it's super simple. First of all, I just call it gradient descent. You have three parameters here: an initialization, right? That w0. Alpha is the step length, right? That thing you can kind of turn up or down, and we can play around with that right here and just kind of see what happens. And max iterations, that's how I'm saying whether or not the algorithm is converged. I'm just running it for a fixed number of iterations and then saying, fine, I'll take whatever you give me, okay? Now, I'm going to record each step, okay, in this container W history, just so that I can plot the result and show you the steps, okay? But the core part of the gradient descent is super simple. This is a for loop, right? I compute the gradient, or the derivative in this case, because it's one-dimensional, right? I take w, I update it as w minus alpha times that thing, and that's basically it. You don't have to record this at the end. I'm just doing it to show you a cool animation, or what I think is cool afterwards, right? But it's literally, you know, like you could say 3 lines of code, okay? You know, it's pretty simple. So let's, hopefully no errors, no whammies, okay? So I've just loaded that into the notebook. I just ran gradient descent. So I ran with 30 iterations as my maximum. I chose the step length just as something small because I didn't know what was correct, and I just chose an initialization at -2. So let's see what happens when I run this thing. Okay, there's my initialization, W0. Travel downward on the tangent line, hop back on. Okay, now I have a tangent line there. Travel downward, hop back on. This animation, we made this specifically to try to illustrate what's going on under the hood of gradient descent. Okay, in practice, this thing runs much, much faster than this. I've slowed down each of the first couple steps so we can see those tangent lines, right? And I can show you the plot, you know, on the tangent line, and then show you the plot back onto the function. Even the steps afterwards, I think the first 4 show you that tangent line, and then it goes like a little bit faster, but not as fast as it would if you just ran it without animating. Okay, and we've color-coded the points from. Okay, you begin at W0 and the point is colored green, and then as you converge or you run out of iterations, you get a color red. Okay, just for visual purposes. Okay. Now you can play around with the step length. Okay, and try to make things say, let's make it too big. Let's see what happens. Okay, we might actually go off the screen. Let's say it's not 0.1 but like 0.8. So I just ran the gradient descent. I have the W history. Now let's animate with each of those steps. There's the tangent line. Okay, yep, we traveled so far that we're off the map. Do you see we hop back on to the right? Okay. But we're still going to make it. All right, 3, we travel down the line, we get back on, we're still cool. Okay, we do a pretty good job. Okay, but let's actually break it. What if we make it too big? Okay, that wasn't big enough to break it. Let's break it. Let's make it 1. All right, let's make it 0.4 or something. If we make it too big, we're just going to fly off the screen, and then nothing's going to happen. Oh, yeah, okay. If we make it too big, actually, also, the function will blow up. Yeah, wait, let me try to make it such that you can kind of see what's going on. That's even too big. Wow, okay. So what's happening here is the algorithm, right? When I made the step size too big, the thing is bouncing around. The steps are going back and forth. It's bouncing around out of control, and you're going to infinity. So that's why I got that error there, okay? The gradient steps are going out of control. Here, hopefully, they'll be a little bit more out of control, but not like so crazy that the computer can't actually compute everything. All right, look, you hopped all the way over here. So that means like the line was all the way down there. Oh, good. Okay, so that's still good. Okay, but you could definitely, absolutely choose a step length that is too bad. I couldn't animate it. We just got an error, okay, when the step length was too big because we hopped around and basically hopped out of this cup all the way to infinity, okay? Now, if you choose so that's if you choose the step length too big. If you choose it too small, you can guess what happens, right? You take little steps and you just don't go anywhere, okay? You could take 1,000,000 steps, right? But if the step length is too small, you're not going anywhere, okay? So we can choose it too small, say like 0.001, really, really small. You see, I'm going to need probably more than 20 iterations to get to the right spot here, right? You can kind of get the sense. And if you make it really small, you're just not going anywhere, okay, numerically. Okay. All right. I'll wrap up. That's a gradient descent applied to that kind of that function where we couldn't actually compute the minimum very well. If you scroll up in this notebook, just because I'm running out of time a little bit. If you scroll up and you look at how this little toy was run, okay, where I showed you how is gradient descent being used. Oh, let's run it again. To actually find the right parameters for linear regression. Let's scroll down. Here you go. Here's the result. You can look at this toy in the notebook. We lay out the gradient descent function, just like for that simple example, as well as the derivatives and stuff like that. This thing, when you run it, so here's the gradient descent function for linear regression. You can see, if you just look at this piece in particular, to fit those parameters correctly, to fit that line, it's exactly the same as the little simple example. I compute the gradient. The gradient is just a little bit more difficult to compute in and of itself, but it's still, essentially the same idea. Then I take a gradient descent step and I repeat that for a certain number of iterations, okay? And if you run that, you'll see exactly what popped out here before. So what was in the background, and I got to load all these cells in, okay? Let's see that, okay. When you run it, this is gradient descent working behind the scenes there, right? That's the thing that's helping you roll downhill in the cost function and thereby tune those parameters correctly. Okay, so I'll let you play with that. And since I'm really running out of time, I'll just show you. Gradient descent is used for another machine learning problem to properly tune parameters called classification as well. That's when you try to distinguish between different kinds or different classes of points. Here I've just colored them, blue versus red. Okay, the simplest case, you want to try to find a line that separates them. And I can show you just a demo that you can play with. It's set up in the same way. We just give you the gradient descent function, okay? And then you can animate the output, the history of each step. And you can see how the line there is being learned as gradient descent finds a smaller and smaller point on the associated cost function. If you want to see what happens with non-convex costs, I invite you to look further on in the presentation, only because I'm out of time. You can just see further on, what happens with non-convex cost functions where you have multiple minima. Well, gradient descent, the short is you just run it multiple times in order to make sure that you find like the best possible stationary point. And there's a toy at the bottom here where you can actually play with that. Let's see, with a non-convex cost function. I think it's at the bottom. There we go. This is gradient descent applied to a wiggly non-convex cost function where you have multiple points where there are zero derivatives, and essentially, like, this is what people deal with when they have to tune parameters for neural networks, for example. And what you do is you just run gradient descent a bunch of times. That's basically the short of it. And you find a bunch of these zero derivative points, and then you just choose the outcome that was the best. Okay. But I think I'm out of time, right?
Maybe time for one question.
Okay, cool. So I know I wrapped up rather quickly. Gradient descent, right? If I would summarize, it's the most fundamental mathematical optimization algorithm, okay, for solving machine learning problems as well as a lot of other problems, okay? You just use the derivative and the slope of the tangent line to basically travel downhill on a cost function. And why do you do that? Because when you derive those cost functions, like you saw with linear regression, and the same is true with classification or neural networks or whatever, you see that you have a function that is a function of those parameters. In the case of linear regression, just the slope and the intercept, that when you minimize it, you get a good fit to the data or a good separation. So that's why you use this like gradient descent algorithm and other mathematical optimization algorithms like that. Okay.
Thank you.
Sure. Yeah, sorry.
How did you make the animation?
Dude, hacked it together. Yeah.
What package?
I'm not using a package. You can look under the hood. They're embarrassingly bad, the way I make those. Just matplotlib, yeah. Yeah, they're bad. They're real bad, but they work, right? Yeah, yeah. Yeah, come see the embarrassing part. Look inside those things. But all of the, so there's Python files. If you go, I should say one last thing. This file, right, is located on this GitHub account. You go to germwatt ML refined, okay, on GitHub. You can find this in the DePy repository. You can see that notebook is there, the presentation's there, then these plotting Python files are there too. So, okay, I'll shut up. Okay.